Assalamualaikum and hello everyone. My name is Alia Fazana binti Abdul Wahab, metric number A211502, and today I am presenting a critical review of an important research paper titled Water Quality of the KLANG River Selangor, Malaysia and Heavy Metal Removal Using Phytoremediation. And this research was originally conducted by Hanafia and co-researchers in 2021. Before I begin, I would like to invite everyone to consider one critical question. Have you ever wondered what happens to the massive amounts of untreated domestic waste, sewage overflows, and commercial runoff from a heavily developed urban centre like the KLANG Valley? Inevitably, a vast portion of it flows straight into our river system, notably the KLANG River. So let's examine the core problem. The KLANG River is a vital aquatic estuary in Malaysia, but it faces extreme anthropogenic pressure due to the rapid, unregulated urbanization and industrialization. The degradation of this river doesn't just harm aquatic life. The accumulation of the toxic heavy metals poses a severe threat to human health through bioaccumulation in the food chain. To address this, the researchers explored a natural, low-cost and sustainable ecology technology known as phytoremediation. This is the process of using green plants to absorb, sequester, and reduce pollutants from contaminated water. In this study, 2 floating aquatic microphytes were evaluated for their cleanup efficiency: Pistia stratotis, commonly known as the water lettuce, and Lemna minor, widely known as the duckweed. Based on environmental issues identified, the study established 2 primary objectives. First, to determine the baseline water quality of the KLANG River across physical, chemical, and biological characteristics. Second, to evaluate and compare the removal rate of heavy metal contaminants using Pistia stratotis and Lemna minor as a phytoremediation agents. Moving on to the materials and methods section. To achieve first objective, the researchers selected 5 distinct urban sampling stations labeling ST1 to ST5 along the KLANG River, each chosen to reflect the different surroundings, human and industrial footprints. The samples were collected 2 times for replication to get more accurate and precise results with 100 mm per sample. First sample was collected during rainy season, while second sampling was collected during dry season. Water samples were analyzed for non-physical chemical parameters such as dissolved oxygen, biochemical oxygen demand, chemical oxygen demand, pH, and initial heavy metal concentrations. Then calculate the overall water quality index or WQI based on the formula given. Microbiological analysis was also conducted via the membrane filtration method to measure total coliform and fecal coliform bacterial units. The researchers chose Pistia stratotis or non-water lettuce and Lemna minor, which common name is duckweed, as a phytoremediation agents to reduce amount of heavy metals that found in KLANG River. For the phytoremediation experiment, the design was executed in the controlled environment mimicking natural light. Both plant species were introduced into separate tanks containing the collected polluted KLANG River water. The temperature dynamic was monitored over a total duration of 21 days with water samples systematically collected and tested at day 0, day 7, day 14, and day 21 to track the heavy metal reduction trend over the time. Now, let's take a look into critical findings of this research. Regarding the baseline condition of the KLANG River, Table 1 shows the average value of the WQI for Station 1 was 74% Class 3, Station 2 was 75% Class 3, Station 3 was 76% Class 3, Station 4 were 81% Class 2, and Station 5 were 73% Class 3. The result indicated that majority of the sampling stations were into Class 3, indicated that water was slightly polluted with extensive treatment required. Next, let's look at the figure 1, which outlines the baseline physical-chemical parameters of the KLANG River. For dissolved oxygen, this is critical for aquatic life. The average was 4.32 mg per liter. Station 5 had the highest DO at 6.45 mg per liter, which indicates the healthiest water oxygen levels, while Station 1 had the lowest DO at 3.12 mg per liter, most oxygen depleted. For pH level, the water was slightly acidic to neutral, averaging 6.67. The highest pH was 7.41 at station 5 and lowest was 5.80 at station 4. For temperature, the overall average was 29.1 degrees Celsius and the highest temperatures recorded at 31 degrees Celsius at station 1, while the lowest was 27.3 degrees Celsius at station 5. For conductivity, the overall average was 233.2 microsiemens per centimeter. The highest conductivity was measured at station 5 with 280 microsiemens per centimeter, and the lowest was at station 1 with 190 microsiemens per centimeter. BOD result shows the overall average was 3.6 mg per liter, and the highest BOD was found at station 4 at 5.5 mg per liter, indicating the higher organic pollution there, while the lowest was at station 1 at 2.1 mg per liter. For COD, the average was 35 mg per liter. Station 1 had the highest COD at 45 mg per liter, highest chemical pollution, while Station 5 had the lowest at 25 mg per liter. High COD occurs due to the high organic and inorganic materials presence. For total suspended solids, the overall average was 64.6 mg per liter. Station 5 recorded the highest TSS at 95 mg per liter, which indicates the high turbidity, while Station 1 had the lowest at 36 mg per liter. For ammoniacal nitrogen, the overall average was 0.67 mg per liter. The highest level were found at Station 4 at 0.98 mg per liter, and the lowest was at Station 1 at 0.32 mg per liter. Moving on to the results of heavy metal found in KLANG River. Table 2 shows that total 19 heavy metals concentration measured in ppb or equal to 0.001 mg per liter for 1 ppb. Now, we look at the elements in ascending order, from the lowest detected concentration to the highest. At the lowest end of the scale, we find highly toxic trace metals like beryllium, cadmium, cobalt, and mercury. These are safely present in very low amounts, mostly remaining well under 1 ppb. In the middle range, we see elements like copper, chromium, lead, and nickel, which generally hover between 1 and 5 ppb. Moving higher up, elements like aluminium, zinc, arsenic, and iron show moderate concentrations, with iron jumping significantly in the second sampling, for example, spiking from 115 to 354 ppb at Station 1. At the absolute highest end of the scale, we have major crustal elements like magnesium, calcium, potassium, and sodium. Sodium dominates the chart, peaking at over 22,000 ppb. Moving on to the biological analysis, researchers evaluated the levels of the total coliform and fecal coliform bacteria across 5 sampling stations to assess the biological health of the river. The results reveal significant fecal contamination, particularly concentrated in the first 3 stations. Station 1 recorded the highest level of biological pollution with a striking bacterial count of 17,500 coloniformis units per 100 mm. Station 2 followed closely behind, showing a substantial presence at 11,300 coloniformis units per 100 mm, and Station 3 also demonstrated severe contamination with recorded count of 10,700 coloniformis units per 100 mm. For discussion of these findings, these 3 specific stations are classified as highly polluted with coliform bacteria. This alarming microbial density is largely attributed to urbanization and human activities near the river, including untreated municipal sewage discharges, runoff, and overflowing sewage systems, often exacerbated by rainfall. As you can see from the graph and figure, the specific heavy metal removal performance over the 21-day experiment, comparing the initial concentrations against the final concentration for both Pistia stratotis and Lambda minor. The initial average concentration of arsenic started between 40.49 ppb at Station 5 and 74.37 ppb at Station 1. After 31 days, Pistia stratotis proved highly effective, achieving a 96.62% reduction and bringing the concentration down as low as 2.17 ppb. In contrast, Lambda minor was significantly less efficient, managing a minor 10.97% reduction. Cadmium levels initially ranged between 0.05 ppb and 0.35 ppb across the station. Both plants successfully mitigated this metal. Pistia striatus led with a 95.65% removal rate, while Lemna minor achieved a highly respectable 93.33% reduction by day 21. Starting with the initial concentration between 1.60 ppb and 2.65 ppb. Copper saw moderate remediation. Pistia striatus achieved a 60.38% reduction, dropping the final concentration to between 1.02 ppb and 2.17 ppb. Meanwhile, Lemna minor removed 35.75% of the total copper, reducing it to as low as 1.24 ppb at station 4. Iron had a relatively high presence in the river water. Over 21 days, Pistia striatus showed a 91.67% reduction. Lemna minor also demonstrated steady reduction, removing 39.97% of the initial content and leaving a final concentration ranging from 218.27 ppb to 237 ppb by day 21. Lead saw the most dramatic and impressive removal rates in this study. Pistia striatus achieved an outstanding 99.24% reduction. Remarkably, Lemna minor outperformed it slightly there, achieving a flawless 100% complete removal of all detected leak at the end of the treatment period. Zinc concentration initially set between 12.37 ppb and 35.52 ppb. It proved to be the most resilient elements to extract for both aquatic plants. Pistia striatus logged its lowest overall efficiency with 32.97% reduction, while Lemna minor achieved a 15.32% reduction. Magnesium concentration were quite high initially. After 21 days of treatment, Pistia striatus reduced magnesium by 53.23%, leaving the final concentration between 1272.81 ppb and 2225.88 ppb. Lemna minor reduced magnesium concentration by 23.81%, pulling final levels to between 2073.44 ppb and 2326.94 ppb. Lastly, mercury started at trace levels and was actively removed by both agents. Pistia striatus achieved a 96.95% reduction, and Lemna minor followed closely with 90.91% reduction, successfully lowering the final concentration to a microscopic range of 0.08 ppb to 0.16 ppb. While both plants are superb candidates for eradicating highly hazardous trace elements like lead, cadmium, and mercury, Pistia striatus is overwhelmingly more effective at treating a wider multi-element spectrum of contamination, especially for arsenic, iron, and magnesium over a 21-day timeline. To conclude, this study presents two main findings. First, the baseline assessment classifies the river under Class 2 and Class 3, indicating slight to moderate pollution, with high coliform bacteria counts confirming significant organic contamination downstreams. Second, both aquatic plants prove to be excellent low-cost solution for water treatment. While Lemna minor achieved a perfect 100% removal rate for lead, Pistia striatus emerged as the more versatile agent, successfully extracting over 95% of arsenic, cadmium, and lead and mercury by day 21. Ultimately, these results demonstrate that using native microphytes for phytoremediation is a highly viable and eco-friendly strategy to rehabilitate the polluted urban river basins. Next, for reference, these are the references that I refer during my reading of the paper research. And that's all from me. Thank you so much for listening.